Okay, good morning. So today I start talking a little bit about the derivative, which is actually a very important part of our lesson, and actually a very important topic in whole mathematics and engineering and in all sorts of applications that you can probably imagine. Uh, so the notion of derivative actually started with probably two very clear questions, one asked by a mathematician named Leibniz, German mathematician, contemporary to Newton, and then the second one, Newton himself. They were actually curious about two different, apparently, so I emphasize here on apparently, they were trying to solve two apparently unconnected, unrelated problems. Yes, one was the problem in geometry, which was probably a mathematical curiosity. And Newton was also thinking about a different problem. He was thinking about how to find the instantaneous velocity of a moving particle. Can I find a way to calculate, or yes, to calculate that instantaneous velocity? So these are two different problems. So let me start with the Leibniz idea, which is easier to grasp here. And then we'll also talk a little bit about the Newton's perspective. So what Leibniz actually was interested in solving was this. Let me try to draw a little bit more careful pictures here. So assume that you have a function and then you have the curve of the function. So let me make it a little bit bigger. So let us assume that this is the x-axis and that is the y-axis. And then you have a function so that you know the graph of the function. For example, assume that this is the graph of your function you are considering, y equals to f of x. And then you pick a point on that curve, say this point. I call it, for example, t here. For the point, for the tangent, you will see why. So I call it t. And then I assume that there are two coordinates. Of course, there are two coordinates for this point because this point lies on this coordinate system. So it has a coordinate, x coordinate. So let me call it a. And of course, you know that what will be the y coordinate, yes? So the y coordinate will be what? If this function is f of x, if I give a to the x, then the y value becomes f of a. Yes, so that is f of a. So this point lies on the curve, and the coordinates are a and f of a. So what Leibniz was interesting to solve is that how can I find an equation for the straight line that is tangent to the curve of this function at that particular point t on the graph. And so that was the question. So he was interested to find an equation for this tangent line. Okay. So this is my tangent line. My goal is to find an equation for this straight tangent line. So the question is very clear, yes? Is the idea clear? So you have a curve, you have a point on that curve, I call it t. I assume that the x coordinate of that point is a. If the x coordinate is a, the y coordinate, because this function is f of x, will become f of a. And then you have this point, and then you draw this tangent line. You are supposed to find an equation for this tangent line. Yes? Okay, how can I solve that problem? Do you remember from previous studies in Math 2C, if you want to find an equation for a line, what do you need? Yes?
K-value.
Yes, you need k value and?
Two different x and y.
So there are two different ways to do it. Either you have 2 points on the line and then you subtract the y's, delta y, and then divide by delta x. So that's one way, but let us look at the other way that actually Oscar mentioned. So we need to have the k value and one single point. Yes, if I give you the k value of my line, so let me write it here. If I give you the k value of my line, and if I give you a point A on the line, say x node and y node, do you remember we had a formula how to write an equation for that straight line? That equation is y minus y node equals to m times x minus x, sorry, k times x minus x node. So do you remember this or not? Okay, so that's an equation for the straight line that passes through this point and has a slope equals to k. So in order to be able to write an equation for the line, you need three pieces of information: x and y coordinates of one single point, it doesn't matter which point on the line, and then you need the k value of the line. Yes? Here in this problem, which one is problematic? Of course, it is clear the k value is problematic because I myself give you a, and if I give you a, you have the function, you put a there, and you find f of a. So this I give you, this you can immediately calculate yourself. So this t that lies on this blue line is already given to us somehow. So the only problem is to find the k value. So if I can find the k value of this tangent line, then of course I can put it in that formula, then I have the equation for the tangent line. So is that clear? Okay. But the point is that it was not probably that easy to solve this problem. Okay. And then Leibniz actually invented a very nice idea how to calculate this. Okay, so how he did it, he said that, okay, let us increase the value of a little bit, for example. So let me, for example, this is a, I changed my color, that's good. So I go to a plus h here. So here, so let me go a little bit further. So a plus h. So it means the distance from here to here is how much? Is h units. Yes? And then try to find another point on the curve which corresponds to this point. Okay? So here, this I call it point A. The x coordinate of point A is what? A plus h. Okay, can you tell me what will be the y coordinate then? F of this number, whatever it is, yes? Okay, and then try to find the slope of this line rather than the target line, yes? So this line, of course, it is clear in this picture, it is not the line that you are looking for. Yes, this line is not, of course, tangent. This line that cuts the curve is called the secant line. Yes? And if I ask you, can you find the slope of the secant line? The answer is simply yes, and the method that Hafsa actually mentioned is the way that we want to use it. So what I want to you for the moment, let us calculate the k value of AT. So let me write this symbol, meaning the k value of the line passing through A and T. So we know the formula. So this is delta. So it is y of A minus y of t divided by x of A minus x of t. Do you remember delta y over delta x? Okay, so now let us put the values that I have here in this formula. So what will happen? Instead of y of A, I put the y coordinate of A, which is f of A plus h. Minus, instead of y of t, I put the y coordinate of t, which you see is f of A. And then instead of x of A, it is A plus h. And x of t is A. Here you cannot simplify any further because I am talking about a generic function. I haven't given you the formula for the function, so you cannot simplify the numerator anymore. But in the denominator, these two a's are cancelled, and what you get is the k value of the secant line, not the targeted tangent line that I am looking for. This becomes f of a plus h minus f of a over h. This is the k value of that secant line. Okay. I think the calculations are very straightforward, yes? Okay, now the point is that, of course, I cannot sell the k value of this orange line instead of this one that I need. But the point is that he observed that if I make this interval shorter, what will happen? This orange line start approaching my target line. So for example, if I try to draw it with a different color here, so for example, instead of taking h to be so long, let me make it shorter, okay? So that's the idea I want you to understand. Might be drawing different pictures by hand here on the board is not that easy, but I hope that I can transfer the idea to you. So let us take h smaller. So what happens, instead of having this as a plus h, let me have this one as a plus h. And I repeat the process, okay? So what happens, it means that I will actually draw this line and find another point. So it means that this point, I call it again A, but of course this A is not that A. Yes, let me call it A again, assuming that instead of having H this much, I have H this much. And then the secant line will be this line now. Yes, so if I draw the secant line from T to the new A, it will be this line, this red line. Still, this red line is not the blue line that I want, but this is a better approximation to the blue one than the previous orange one. Yes, so this, but if I ask you calculate the k value of the red line, of course the values are different, but the formula is the same. Yes, because I am taking this to be my new a plus h, everything will be repeated and I will get the exact same formula with different values of h, of course. So if you take h this much, you will get the k value of the orange line. If you take h this much, the same formula gives you the k value of the red line. Yes? So, but the idea is now hopefully clear for you. So even if I make this a little bit smaller, what happens? So this means that then I will have a point here. Yes, if I make it smaller. And if I draw the new tangent, the new secant line, it is even closer to my target line. Yes, so that is intuition. I'm not proving anything. I'm just trying to define something and I'm trying to make it intuitively plausible, not rigorously, because the logic will be the other way around later. I can talk a little bit about that logic, but I want you to understand that intuitively this seems to work. It means that if I make h smaller and smaller and smaller, this secant line starts rotating about the point T and becoming closer and closer to my target line, the blue line. Is that clear intuitively or not? Okay, the ideal situation is when what happens? H is 0, but there is a problem. H cannot be 0 because unfortunately it happens in the denominator. So what can I do? I can use the notion of the limit which we developed actually in the previous lessons. So this means that, I'm just telling you again, this is intuitively plausible, that the k value of the tangent line that I am looking for seems to be equal to the limit of the secant line, the k value of the secant line, when what happens? When this value of h approaches 0. So is that clear? This is just, I want you to intuitively understand. Yes, rigorously it's a different story. But intuitively I don't think it's hard, yes? Is that clear? So it means that, what does it mean? It means that if I make this h smaller and smaller, this new point becomes closer and closer to this original initial point. Then it means that this point, instead of a having been here, it becomes here, then it becomes here, then it becomes here, and then if I start drawing these secant lines, they're actually turning around T, being closer and closer to my target line. Yes? Again, I'm just emphasizing, I'm not proving anything. I'm just trying to motivate you, or I just know reason that this seems intuitively understandable. Yes? Is that clear? Yes or no? Okay, so that's it. And actually, k of tangent is equal to the limit of, instead of k of at, I put that expression, h goes to 0. So more or less, he found this formula for the k value of the tangent line. Okay, so actually, this is the reason that in principle limits become important. People didn't know about limits. They wanted to calculate this, which is a geometrical, from geometrical point of view, it's very simple. And the notion of tangent was also known to ancient Greeks. Yes, they were trying to draw tangent lines, for example, to circles. So it was actually a mathematical curiosity. Can I find a formula so that if you give me the formula for the function and if you give me a point on the curve, then I will be able to find an equation for the tangent line to the curve at that point. That was a question. Yes, mathematical curiosity question. Is that clear? Okay. So by the way, let us try to see, let us do it in a practical problem, yes? For example, let me give you a function to see that this really works, okay? So let me write an example here. Determine, this is a typical, by the way, I put a star on it because I really want you to understand this problem in a very good way. It's very simple. I'm emphasizing it on it not because it is hard, because it's a very typical problem. So determine an equation of the straight line that is tangent to the graph of the function. Let me make it simple. Of the function, a very simple function, f of x, x squared. Probably this is the simplest curved function ever, yes? Because if I write f of x equals to x, then it becomes a straight line. And the idea of having a tangent line to a straight line probably is not that intuitively clear. So determine an equation of the straight line that is tangent to the graph of this function at the point on the curve, at the point on the graph whose x coordinate is what? So let me, for example, say 1. Yes? Yeah, we want to use the definition, yes? For the time being, we don't have any formulas. If you're using the formulas, that will come later. So determine an equation. Is the problem clear? So if I want to try to make you understand this, I would say that, okay, let us have a picture here. The graph of f of x, x squared is very famous, yes? So something like this. This parabola is that function. And the point y, x coordinate is y, so this becomes a point here. And at that point, I want to draw a tangent line. Of course, the tangent line goes forever from both sides. I want to find an equation for this tangent line. So that is intuitively, this is what I'm going to do. Is that clear? Okay. So what I do, first, I can find the coordinates of this point, because in writing an equation, to write an equation for the curve, for the tangent line, for any line actually, I need two pieces of information. They are here. I need to know coordinates of one single point, whatever that point is, doesn't matter, but it should lie on the line that I am going to find its equation. So, and then I need to find the k value. For finding this point, I will take this point. By the way, there is a name for that. That's called the point of tangency for obvious reasons. This is the point of tangency. They have given me 1 here. So what is the y coordinate for this particular case? It's again 1. Yes, because I put 1 into the function. 1 to power 2, which becomes what? 1 and 1. So the problem for these two are solved. So I know that y naught in this problem is 1. X naught in that problem is coincidentally 1 again. So what is left for me to calculate is the k value. And for finding the k value, I use the idea of that formula up there. So let me just write k, instead of writing k tangent, because I am talking about the tangent. So let me just suppress the subscript. The k value, let me write the formula. And I really want you to respect and memorize this formula for the happiness of the soul of Leibniz, yes? Because everything in your life depends on this question. It changed the human history, by the way. We will come to that. So this simple question changed everything. So, so this is good to understand. So if you ask a good question, so that's actually life-changing. Okay, we want to calculate this. This is technical problem. So I want you to learn this because this is needed. How can I calculate this limit? First of all, you need to adapt. You need to write this limit in the problem that you are working in, okay? So in that context. So you need to write this limit, h goes to 0. The denominator is h. But the numerator, instead of here, I have to calculate a. What is a here? 1. Yeah, so this becomes f. Let me be patient and write everything. First, I replaced a with the given number 1 in the problem. Okay? Now I continue a little bit further. I need to calculate this part, and I need to calculate this part. Very easy. So I hope that you remember. If I want to calculate f of 1, I need to go to my function here. Yes, I need to go to my function, replace x with 1. So let me write everything in detail. So this becomes 1 to power 2. But can you tell me what happens for f of 1 plus h? What is f of 1 plus h?
1 plus 2h plus h.
No, it's step by step. So this is your input, yes? This tells you that if I put the input x, the function will take that input from me, square it, give it back to me. So here my input was 1, the function did the same. Take that input from me, square it, and give it back to me. Now the input is what here? 1 plus h. So the function will do the same thing. It will take this one from me, square it, and give it back to me. And then the denominator is h. So just let me know if you understand this or if there is a problem here. Anyone understand? Any problems here? Okay, but then this is probably a very simple limit for you if you have done your homework properly before. So this is a very, very simple limit. And yes?
Why did you square it?
No, because the function is x squared. Yes? Okay, so this is a very simple limit. I told you that whenever you want to calculate limit, you need to check the value first. But then this is one of those cases it is problematic. And don't check it, it's always problematic. Because if I put 0 instead of h, the numerator becomes f of a minus f of a, which is 0, and the denominator becomes also 0. So this is always indeterminate 0 over 0 when you are calculating the limit for the derivative. Okay. But then I need to simplify that. I hope that you know what to do because you already had the exam for this. So what should I do? Expand, simplify. So the first one is squared 2 times the first one times the second one is squared. And then minus 1 to power 2 is just minus. And then 1 to power 2 is 1 divided by h. H goes to 0. Yes? And then this 1 and that 1 are cancelled. So this becomes the limit 2h plus h squared over h. H goes to 0. But I factor h out in the numerator. But then this h and that h are cancelled. So this becomes the limit of 2 plus h goes to 0. And then the answer becomes 2. So the k value of that tangent line is indeed 2. And then everything is ready. So let me write the answer here. So y minus y node, what is y node in this particular problem? It is the y coordinate that I got here. K value, I got it here. X minus x node, which is also 1 in this problem. And I prefer to simplify it a little bit. So this becomes 1, 2x minus 2. Then I move minus 1 to the other side. So this becomes 2x minus 1. Yes? So if you want to write it in a different form, you can also move y to the other side. It doesn't matter how do you write it. That's completely okay. That is also the general form. That's also okay. So this is an equation for that tangent line. Is that clear? So it is not hard, but you have to calculate this very particular limit every time for calculating the derivative. It's not the derivative. The derivative will come later. For calculating the tangent, the k value of the tangent line. Is that clear? So at least it is practical. Yeah, we can do it at least for this very simple case. Any questions? Okay. Because today I have to finish the lesson very early because you have to leave the aula because there is a very big test here. So I want to not to continue here. I want to understand the other perspective that Newton was interested in. Okay, he was interested in apparently completely different problem. It's clearly different because he was interested to know how to calculate the instantaneous velocity of a moving particle, which is completely different problem than here that I mentioned. Here I want to find an equation for the tangent line to a curve, which is probably in the realm of mathematics in your imagination, but that was a practical physical world in the outside world. So you want to measure you need the instrument. You want to calculate the instantaneous velocity of a moving particle. But let us see what happens if you want to do that. So I don't know how much you know about physics. So let us consider that your moving particle, this is the x-axis. Okay, no, let me call it, x-axis. And then you have a moving particle. And this is the origin. So assume that for simplicity, your particle is moving in that direction. But it can accelerate or decelerate, so it changes the speed. Okay? And then because I am just trying to talk about this particle moving in that direction, I can interchangeably use the word velocity and speed. Because velocity, it should be directed, but I am assuming that this particle is going in that direction forever for simplicity. So it doesn't matter if I use the word speed or if I use the word velocity. Yes? Okay, so what I want you to understand is that assume that your particle at the initial time that I start the experiment is at the origin. Okay? Okay, when time is 0, the x-coordinate of this point is also 0. I'm assuming that the particle starts from here, then I will actually start the clock or start the watch, and then I see what happens. Okay, and then I would say that at a later time t, the position of my particle is x at t. First of all, do you understand this is happening? Yes? Because the x position of my particle depends on at which time I am looking at it. So the position of my particle is a function of time. By passage of time, the position of my particle on this axis is changed. Yes? So now let us see what happens. Assume that here, this particular time is t node. I want to know the speed of the particle at this very single instant of time, okay? And assume that I give you how this particle moves as a function of time. So I give you the function of position of the particle as a function of time. So at any instant of time, you know where the particle is. For example, I say that, okay, this particle is moving in this way. yes? And I say that, okay, when the particle, of course, let me write it plus t. Where is the particle at the initial time? You put 0 instead of t and you calculate, the answer is 0. So if the function obeys this rule for its position, at the initial time, it is really at the origin. But if I ask you, where is it 1 second later? You put 1 instead of t, what do you get? 2. So this means that 1 second later, the particle is at 2. But let me go 1 second later. So x of 2, yes? What happens? You put 2 here, 4 plus 2 is 6. So it is clear that the particle is not moving with the same speed. Yes? Because in this 1 second, the particle moved 2 meters. But in this 1 second, from second 1 to second 2, the particle moved 4 meters. So this means that the particle's speed is changing. Okay? And that's the problem. Even though the speed of the particle is changing, I want to answer what is the speed of my particle when time is exactly 1 second, or when the time is exactly 2 seconds. So we want to answer this question. Is that clear? Okay. But Newton actually approaches this problem in a very similar way that actually Leibniz approached that problem. Because he said that I don't know the formula for the instantaneous speed, I want to discover it, but I know the formula for the average velocity. So he said that, okay, let us wait h seconds. I am interested to find the speed of the particle at this time, but let me wait h more seconds. So the particle will be somewhere else. So when time here, the time is t naught plus h. Okay? The position of the particle here is x of t naught. The position of the particle here is x at t naught plus h. Is that understandable what I'm writing on the board? Yes or no? Okay. Okay, now if I ask you what is the average velocity of this moving object on this time interval, what do you say? What is the average velocity formula in physics? You calculate the displacement divided by the time interval that displacement happened. Yes? So the time interval that this displacement happened is how much? The time.
Delta t.
No, not delta t in this picture. I told you how much you need to wait? 8 seconds. So what is the time interval from t naught to t naught plus h? It is 8 seconds. So this is the time interval. Yes? And then what is the displacement? From here to here, it is x of t naught, because the time here is t naught. From here to here is how much? X of t naught plus h. But you are interested in the displacement. So what do? You subtract these two values. Yes? So this becomes x of t naught plus h minus x of t naught. So this is not the instantaneous speed. This is the average speed. Yes, let me write V average. Okay? This is the V average. But how can I find the instantaneous speed at this particular time? By making this time interval again shorter and shorter. Yes, because if I wait a long time, this particle has a lot of degrees of freedom to change its speed up and down, yes, because there is a big time. But if I make this time shorter, the chances of this particle changes its speed from that moment is lower, yes? So for example, if I wait for 10 seconds, it is imaginable that the speed of the particle in these 10 seconds, the average speed is not very close to the speed that I had here, because the particle has enough time to change its speed, yes? But if I wait 2 seconds, still the average velocity is not the same as the speed that I want to calculate. But hopefully you agree with me intuitively that the average speed in this shorter interval is closer to the speed of the particle at that time. Because whatever speed of the particle was here, the particle has only 2 seconds to decide to change the speed. and that time interval is shorter. And if I make this interval shorter and shorter and shorter, okay, this what happens then? The average speed becomes a better and better approximation to the speed at this point, intuitively. Is that understandable? Yes or no? Because even if you are a photon that you can travel the speed of light, if I give you 1 billionth of a second, then you do not have you don't have a chance to change your speed. You know that much. If you have that chance, I make the time interval even shorter. Yes? So that is the idea is this. I hope that you understand that the instantaneous speed at that moment of time is equal intuitively of this average speed, but when the time interval goes to 0. Understandable? Okay. Now, if I write this, v of t node is equal to the limit, instead of v average, I put that expression, divided by h, and h goes to 0. So this is the formula that Newton probably found for calculating the instantaneous speed of the moving particle. That was the formula that Leibniz found for calculating the slope of a tangent line. These two problems seem to be completely unrelated. But I hope that you agree this mathematical structure behind them are the same. Yes? What is the difference between this formula and Leibniz formula? That's just a matter of names that I have used. Yes? In that formula, f was more common because he was working in mathematics, and variable h or a he used. So here I would use t node because I am talking about time, so using t is more. But I mean that hopefully you understand this structure of mathematical structure of this and that are completely the same. So this means that this is actually very exciting, by the way, if you think yourself from a philosophical point of view. These two problems are completely unrelated, but if you want to do the mathematics of those problems, they're actually giving you the same ideas. And something like this when happens, this means really there is a deeper concept going on here that we have to discover. So this is not a coincidence. And then after that, you can have millions of examples that this notion comes in. So this kind of limit appears in mathematics so much that mathematicians probably got tired and tried to say that, okay, let us give it a name and try to understand this better. And this is the way mathematics works, okay? So this is just two examples. This is very good, by the way, because these are two unrelated, apparently, problems. But when it comes to its mathematics, they are completely the same thing. Okay? And then, so from now on, this is why I'm saying that these questions are life changers. Because, for example, later, Maxwell, he was able to write his 4 famous formulas for electrodynamics. Okay, so they are also involved with the notion of derivatives, but much more complicated version of the derivatives. And those equations gave rise actually to discovery of electromagnetic waves. Okay, so he was able to do mathematics and be able to predict that electromagnetic waves should be a reality. And then later people actually discovered that. And then hopefully you understand that everything after that, everything related to electricity is really, really based on those equations. So this is why I'm saying that this is life-changing, to take electricity, take this derivative. This is called, by the way, then the mathematician called this limit the derivative. Okay? Now we'll talk about that later. So if you take the notion of the derivative out, then it means that at least you have to get rid of those Maxwell's equations, and then you lose the notion of electricity. And then you can guess what will happen. So what I'm saying is that's really true. So at least you can actually cherish the soul of Leibniz and Newton by memorizing them, even though these formulas are always actually in the formula sheet. Okay? So today's lesson, actually I didn't want to spend so much time on details, but I want hopefully that you understand that we had 2 problems. One problems in geometry, one problems in physics. We stated the problem and tried to solve them. Both of them gave rise actually to the same kind of mathematical process and finding this limit. Okay, so next lesson I will actually talk a little bit about these, because there are two things you need to understand. First, you need to understand the concept. That is good. On the other hand, you also need to be good in calculating these kinds of limits. Okay, so one is concept and one is a skill to improve your techniques. We will work on both of them. But this is the very serious mathematics that you are facing. So that is the branch of mathematics called calculus. Okay, the calculus has two main ingredients. One of them is called the derivative and the other one is called integral. And again, Newton actually realized that there is a big connection between these two. People didn't know about that because for integrals, they want to calculate the area under the curve, the area of objects. And this problem, the derivative is related to these kinds of problems. Newton realized they are interconnected. So the notion of area is somehow related to the idea of the derivative. We will come actually to understand these things better in the new future lessons. Okay, any questions so far? Okay, I cannot write something on the Google Classroom because I didn't follow any pages, but I want you to to understand what is the notion of a derivative. Okay, if you don't have any questions, we stop here, and if you don't mind, you can, please leave the aula so that I can prepare it for the exam. Thank you.